the radio bands with wavelengths in the area of 1 meter and above. It's in the area of 100 megahertz. Here we have 2 to 6 gigahertz. Then 3 decades down, we have the radio frequencies, then long wave, and then. So that's
the light.
That's the light. That's what we call the electromagnetic spectrum. Yeah. So in a very short or a very small portion of the whole spectrum is visible to humans, and that's what we call light in the common sense. Yeah. But it's nothing deep, nothing special. It's just a small portion of the electromagnetic spectrum. And where it comes to the solar cells is if you hit the solar cell with a radiation of these ISM bands, for example, yeah, then it won't generate an electron-hole pair. The problem is that with the frequency there is also energy linked. And the energy of our radiation you can calculate by h times nu, and nu is just the frequency of the radiation. Yeah, this is, but you don't use the letter F. In quantum physics it's nu. So that's not a V,
Yeah.
it's a Greek letter. Yeah. So that means the higher the frequency gets, the higher is also the energy. That's why X-ray will kill you and ultraviolet radiation will only destroy your skin.
Only.
And cosmic ray or gamma ray
Will destroy the world.
will kill you immediately.
What is H? What? Energy?
That's the Planck quantum. That's a constant.
Okay.
It's a constant. Yeah? The Planck constant.
So what is the best frequency or the best wavelength to this cell for?
The solar cells actually are optimized for sunlight because there's the most radiation here on Earth comes from sun.
Yeah, but
we'll go through that a little bit later. So they are optimized for this frequency area here.
between blue and red.
Blue and red.
Yeah. Because I saw
But
in.
also ultraviolet will give you a huge amount of energy. But there is the atmosphere that will cancel out the ultraviolet radiation.
Because I saw there is a map on the world for the sun, the direction of the sun for each place, but I didn't understand why here is better than here.
Yeah.
The sun
We'll come
everywhere.
to that a little bit later.
Okay.
If we focus on the mechanism. But the solar cell will give you energy for any kind of radiation higher than roughly 800, maybe 1 millimeter, one micrometer, excuse me. But it definitely won't give you any energy for ISM bands, because it's way too low. And that's the physical effect that is responsible for that is the photoelectric effect. That's what Einstein got his Nobel Prize for.
Yeah.
And this photoelectric effect says that you can only get the electrons from the valence band to the conducting band, and that's what we have to do for a solar cell. We have to get the electrons from here to here, and you can remember the energy gap is 1.1 electron volts. That means our irradiation must be of a frequency that gives us more energy than 1.1 electron volts. And that means we have to be in that area here. Up from here, every kind of radiation will create your electron hole pair. But below that,
Nothing.
I don't know if it's here or here, huh? Somewhere in here. That's the absorption edge. That's the absorption edge. So if the energy is bigger than 1.1 electron volt, it will create an electron hole pair. If it's below that, nothing will happen. And the funny thing is, and that was the big finding of Einstein, it's not a matter of how long you let the radiation shine on this p-n junction. It's only a matter because energy is transferred by energy quants. So it's one photon that carries the energy. And the energy of one photon is not added up with the energies of other photons. Huh? So the energy must be delivered by one single photon, otherwise it won't work. That means it's not possible to have lower energy, but increase the intensity of the radiation. That doesn't work. It even works with one photon. One photon creates one electron hole pair. Yeah? And that's a strict relation to that. You cannot create one electron hole pair out of two photons. Yeah? That doesn't work.
One photon, one electron.
One photon, one electron. Yeah? And that's why if we are talking about sensors, for light sensors you have a fantastic linearization between incident radiation and generated electrons, because one photon creates one electron. And that's the photoelectric effect by Einstein. That means your incident radiation must be of a certain frequency or above. If it's below that limit, then the solar cell doesn't work. So that means you have to find a material that fits to your sun spectra. And with silicon you can do that. So most of the solar cells are out of silicon material. Okay. So then we can think a little bit about, because we have pretty much technical aspects, how much energy do we get out of solar cells? Or do you have any idea how much energy it's transferred from the sun to the earth?
How many energy?
Yeah, much. At least much. But any numbers or ideas? From the one end we got the sun.
We don't know, come on.
Let me check, maybe I know.
And far away we have the earth. So it's not the correct scale, because otherwise we have to draw the sun something like that. So there is an energy flow from the sun in every direction around the sun, and only a very, very small portion hits the earth. And if you scale that down to 1 square meter, then an energy of 1.35 kilowatts per square meter. That's what the sun gives us. Yeah, so that's a huge amount of energy. But the problem is that this so-called solar constant is measured in the outer sphere of the atmosphere. So it's the outer layer of the atmosphere, and the atmosphere is roughly around 8,000 kilometers, and that's where the solar constant is measured, normal to the direction of energy flow. So if you put your solar panel in a height of 8,000 kilometers, normal to the incident radiation, you will get an energy of 1.35 kilowatts per square meter. So that's pretty much. So 3 square meters should fit for one household. But the problem is, how do you get your panel up there, and how do you get the energy down here? So if we go down to the surface of the Earth, then we lose roughly about 60 to 70% in the atmosphere. And
From the ozone.
there's a huge dependence. Now, the ozone is not so much the problem, but it's diffusion, so that the radiation gets diffused to every direction. That's why the sky is blue, because the blue wavelength, or the blue light, has the most of the strain.
Why again? I'm sorry. Why the
That's
sky
why
is
the
blue?
sky is blue.
Why?
Because for red light, the stray coefficient, maybe you have some air molecule, so the light is straight in all directions. But the lower the wavelength, the lower the strain of the beam. That means the red light got only a little strain, and blue light is nearly down
Reflected.
to every direction. Yeah? So if you're looking up into the sky, the red light travels through the atmosphere and hits the surface, and the blue light got straight to every
Where?
direction in the atmosphere. And that means if you look up into the sky, you see all the blue lights. Because they're straight. That was a common problem of physics until 1700, something like that. Because no one could explain why the sky is blue.
So it's known from 1700.
Yeah.
And we don't know it.
And you don't know. So the problem is the stray coefficient of light. And the strain increases with frequency. So the higher the frequency, the more strain you get. That means, for example, that's why the sunset is red. Because all the blue light has disappeared. Huh?
Yeah.
So if you got a red beam, let's say this is the atmosphere of the Earth, and there is a blue beam, it will get straight within the atmosphere, and the light is straight to every direction. Yeah? And the red beam get also straight, but only a little bit, so that it travels much more through the atmosphere in a linear fashion. Yeah? The blue light is straight in every direction, and the red light is traveling longer in the original direction. That's why during midday the sky is blue, and during the evening times with sunset, if you are here, then the way of the light through the atmosphere is very long. So all the blue light gets straight out, and only the red light remains. And also, the more polluted the atmosphere is, the more beautiful the sunset will get, because the pollution is causing the straying of the light. Yeah, so the clearer the atmosphere, the bluer the sky. It's also some common knowledge. Eh? Okay, so if we start here up in a height of 8,000 kilometers, we got a solar constant of 1.35 kilowatts per square meter. And the more we go down to the surface, the more energy we lose. So there are different loss factors, and the loss factors depend on the geographical position. Eh? If you are along the equator, then you are lucky, at least for solar energy, because there the loss is around 0.7. For European countries, we are up here. What remains is a factor of 0.3. And north of Europe, it doesn't make any sense to use solar energy. So up here it's worth it. And also the irradiation angle, if you're at the equator, then the angle is nearly 90 degrees. You have
the best solar
the
energy.
best efficiency. So that means if we are in Europe, the energy that will enter our solar panel is the solar constant multiplied by our loss factor, 0.3. And then we have the efficiency of the panel. How big is the efficiency of a solar panel? Any idea? 80%?
40%.
40%?
Depends on the material.
Depends on the material, eh? And there is also some reflection on the top layer of the solar cell that also decreases the efficiency. The efficiency is around 10%, a little bit more, 12.
That's the best efficiency we could
That's
have.
the best efficiency we currently get. But there are some works done by the Fraunhofer Institute. They build a panel with 40%. But that's not in production now. The panels you can buy now give your efficiency roughly about 12%. Yeah. So what's the time?
3:20.
It's
So
15.
we already
17.
skipped a break.
Yeah.
So we do it like the last time.
Okay.
So let me know when it's finished.
Okay.
But I don't have.
Okay. We finish at 16.
3:40. Yeah,
What?
3:40. When does the hour finishes?
I don't know.
Four.
At 4. Then
At 4 o'clock, so 3:50. Yeah.
50.
I stop writing now because
So if you are using a solar panel, and in Sensorics it's very common that you use a solar panel, because if you are monitoring some environmental conditions and you are somewhere in the woods, then you don't have a power source. The only thing you can rely on is a solar panel. But there are also some different possibilities of harvesting energy. The best one and the most popular one is to use a solar panel. But there are also some other possibilities. You can use vibrational energy. So that means maybe if you're doing some traffic monitoring or railway monitoring, you can use some piezoelectric cells, because when a train moves by, then there is a lot of vibration in the in the tracks, and if you attach your harvester at the tracks, then you can harvest, but that's not very much energy. It's in the area of microwatts. Yeah? With a solar panel you can get out watts out of there, 10, 50, 100, depends on the area of the panel. Vibrational energy gives you some microwatts. Then obviously, since every area is covered by mobile communication, you can get the energy out of the electromagnetic spectrum.
That's currently new, I think.
That's currently new, but it gives you only some picowatts. Yeah? That means it's nearly not much in there, but it's a possibility. Yeah? If you are maybe in an area without sunlight, maybe somewhere in the north of Russia, where it's not useful to use solar panels, then maybe it's an idea.
Or we can combine them.
Or you can combine them, yeah, that's the best way most of the time. And any other ideas?
For how we get energy?
Yeah.
The third one is EN.
Electromagnetic spectrum. So you can remember there was the visible light and upwards we use for the solar panels, but you can also go downwards to the ISM bands or radio bands, but it's very less energy in there. But thermoelectric.
Yeah.
Energy can give you some microwatts. Yeah. Seebeck effect and all these things, we will come to that in the sensoric lecture, but I will give you, these are the four main possibilities to harvest energy out of our environment. If possible, use the first one. Yeah? That's the most established and the easiest. Vibration, it's also possible, it depends on the application. If you are monitoring highway noise, then you can use vibrational energy because there is enough noise and vibration there. For the solar panel, there is also some guidelines you have to follow, because the solar panel works like a normal battery, with one exception. The energy that is generated is strongly dependent on the radiation that falls onto your panel. That means what you should do, but that's very expensive, your panel should follow the sun. Yeah, you have to find some way of mounting so that you can follow the sun as the sun is traveling across the sky. Then you should mount your panel so that the incident angle is 90 degrees, because this gives you the best efficiency of the panel. But sometimes this is really hard to achieve. There are some other options that you use more than one panel so that you can follow the sun. So in the morning you use this panel, around midday you use the second panel, and in the afternoon you use the third panel. Obviously that costs you more than one panel, but then you have to judge if it's worth to implement a sun tracker or just to use 3 panels.
What gives us the most?
The sun tracker will give you the most.
Yeah.
But 3 panels is also not that bad, because you can use all 3 panels in parallel. And even if the sun doesn't hit your panel, remember the stray light, there is also some radiation onto the panel.
So what's going on if we're using the care panel? Is there any possibility to use the care panels too?
Sorry?
The care panel.
curve. If you cannot follow the curve,
We cannot follow that.
then use more than one panel. One bad thing is if you are behind the building. That's not the best solution, because then there is even no stray radiation. If you're directing your panel to the blue sky, then your energy will be maybe 1/100th of the energy with sun radiation, but it's still 1/100th, and that's okay. But if you're behind a building, then you are losing nearly all the energy, because there is no light anymore here. And there is another thing with the panel. So there is the current that we can get out of the panel, or we begin with the other, with the voltage that we can get out of the panel, and the current that we can get out of the panel. That's the load line of the panel. And the load line, normally the more you load the panel, the lower the voltage will get. And normally it looks something like that. If the radiation drops down, then the curve will look something like that. Maybe here we got 20 volts. That means if you are charging a battery, maybe it's a 12-volt battery, you cannot just connect the panel to the battery. That will ruin the battery or the panel, depends. Because here we got 12 volts. That means you charge the panel all the time with nearly the maximum current. That will ruin the battery. And it's not the best operating point. It won't give you the maximum power of the panel. Where can you see the power the panel gives you? Let's say for this point here, the area of the rectangle is the power that the panel will give you at the working point 1. And our goal now is to design the loading of the panel in such a way so that this area will be a maximum. That's a pretty complicated task, because you have to monitor the current, the operating current, IC, and the operating voltage, UC, multiply them, and the product will give you the power you can draw from the panel. So you need a microprocessor for that. Because if you are here, if you're at that operating point, you will see the area is quite different. But there is a simpler solution. You can use an integrated circuit that does the work for you. So the way is the solar cell, the integrated circuit, or the panel manager, and then you have your battery, your 12-volt battery, and your sensor you connect to the 12-volt battery. And this controller here, most of the time, it's called an MPPP. That means a maximum peak power tracker. That means depending on the irradiation of the sun, this circuit varies the load of the panel in such a way so that your operation point will give you the maximum power out of the panel. And normally you don't have any power to waste. So if your panel is generating too much power, then you are using a smaller panel. So the design is always to get the least area for the panel, because the panel area costs you.
Where is this point exactly? Sort of.
Maximum.
This you can,
No, this one?
measure current
Maximum
and
power.
voltage, build the product,
Okay.
and this gives you the power. And then you have to do some small variations around this point and to see where is the maximum. So it's an optimization process. But it's not, normally in practice, it's not that difficult, because the manufacturer of the panel does this calculation and gives you the maximum peak power point for the voltage. So there is also, if you look at the panel, there is the open loop voltage, the short circuit current, and the maximum peak power voltage. Maybe it's 18 volts. So then you have to design your circuit in such a way that your panel, that the voltage at the panel is at 18 volt all the time. And that will give you not the exactly maximum peak power point, but it will give you an optimum roughly around 80 to 90% of the maximum peak power point.
And that's enough, I think.
And that's okay. Yeah. Because this, it's an integrated circuit, you can buy, build some circuit board, and it's quite easy. Okay, I think
We have 20
we
minutes.
get drowsy, so maybe we,
Yeah.
are we done, or
We have like 10 minutes.
you run out of memory? Or?
Yeah.